Hey guys, Joseph Moore here, and I decided to do a little thing called Project Euler I'd like to show you. Now, this is my second time doing this because the audio in the first video didn't kind of work out. So here I'm just going to demonstrate to you how I got this answer right. That kind of spoils the surprise, I guess. But here, let's just look at this code which I came up with to do the problem, and we'll go with it. Alright, so this is basically what I did. Everything you see that has time in it, this is just for taking the time. Basically, I'm importing the module time, and this allows me to calculate how fast it took to complete the program that I did. So this right here is merely for calibrating how much time it takes to do the time. And this is used in right here, this line here, here, and here. And this line basically means print what the current time is minus the time that we started out at minus however long it takes to do the time stuff. So this will give us the actual time that it took to do the program stuff inside. Alright, so this is basically how the code works. There are three methods that I chose to work with. The first one is brute force, and right here I have a rolling sum, which is what I'm going to be continually adding to. And right here we have a for loop, and we're doing for some iterator I in the range 1000, which is basically a list of 1000 numbers 0 to 999. So this works for the below 1000 criteria because it doesn't include 1000 itself. And then for each number in that, we're checking if that number divided by 3 gives no remainder. That's basically what this percent sign means. That's the modulus operator. So if the number modulus 3 is equal to 0, meaning that it's perfectly divisible by 3 and it gives no remainder if you divide it by 3. We're saying if that is 0, if the remainder given to that number divided by 3 is 0, or if that remainder given to the number once divided by 5 is equal to 0. If that's the case for the number I, then add it to the rolling sum. So this is basically the equivalent of going through each number. 1, is it divisible? 1, well, that's not divisible by either. No. 2, that's not divisible by either. 3, that checks because it's divisible by 3. 4, no. 5, yes. 6, yes. 7, no. 8, no. 9, yes. 10, yes, etc. So this one will pretty much guarantee us the right. Excuse me. There's someone calling my name. What do you want, John?
I got my head stuck in a knot, and no one can undo it.
You can.
No.
You got yourself into it.
No, Mom tried. She couldn't do it.
Well, that's your fault for tying a binding knot. And I guess you're just going to have to live with that around your neck for the rest of your life. John, no, don't cut it open. Fine, I'll untie it.
Thank you.
Excuse me. Can I see the knife?
No.
I'm not going to.
You're going to
cut
stab
it.
me.
I'm just going to loosen it with the knife.
Oh. Well, yeah, I knew you were going to do that.
Well, you can just take it off your neck.
No, it won't fit.
Yes, it will.
It won't.
Yes, it will.
No, my cranium's too big. Oh, God. No,
Oh,
Joe.
jeez, you're actually right. Okay, let's see it.
No. I want to get the knife.
Here, get the knife.
Yes.
It's on the ground, right by your feet.
Very safe place to put it.
Yep. You're fine, Jen. Safe hands.
No, I'm not. From the man who cut my thumb open, I don't think I should trust him with a knife.
Oh, you're fine.
Oh, God. Oh, God, he's cutting downwards now.
Don't actually use that. Maybe if we I'm using it right there.
Okay.
Don't use a knife. It's too dangerous.
From the man who cut my thumb open.
Yes, using the knife is too dangerous. That's kind of part of the reason why I think so. Alright, now see if I can you find a pencil? That's a bit safer.
Pencil. Yeah. Maybe you should.
A pen would work as well. Alright. See what we got.
I'm afraid.
This to give us a bit of leverage. Let's open this part up right here.
Yeah, I tried using a fork knife, but
A fork knife?
yeah.
A knife for cutting forks?
No, a fork for stabbing or cutting knives. Are you?
Wouldn't that be a knife fork then?
Why are you always talking to Faith?
What are you talking about? I'm not always talking to her.
Oh, really? Yesterday.
That was the first time in a while. You know, my phone's not working.
Why
It
isn't
needs battery.
Oh, that's a good reason.
Oh,
Am I gonna be stuck here forever?
no. Here.
I'm like, Dobby, this burns. It burns.
Don't you mean Gollum?
No,
I
Dobby.
got it. Don't worry.
It burns. It burns.
Bobby never said that, though.
Yes, he did.
That was Gollum.
No, Gollum.
Dobby's a house elf.
Oh, thank you.
I apologize for that small disturbance. I will cut it out. I'm sorry, I just had a small thing to go with. So, that's what this first brute force method is. So, let's go into the next one, which is the built-in sum function. So, right here, I'm printing... John, what are you doing? Yes, you are. You're tying my door shut. Stop it. Oh my god. I'm sorry about that. I was distracted by my brother. So let's see. We got the second method, which is using the built-in sum function in Python. So we're taking the sum of the range from which is basically a list of all the numbers between 0 and 1000, not including 1000. And this 3 right here means we're taking every third number. So we're taking the sum of that and we're adding that to the sum of the range from 0 to 1000, not including 1000, taking every fifth number. And because when we do that, we include numbers of like 15, 30 twice, because this will count 15 and then this will count 15. Because we're adding that twice, what we need to do is subtract one instance of that, and that's what this does. We're subtracting the range from 0 to 1000, not including 1000, of every 15th number. So that's 15, then 30, then 45, then 60. We're subtracting all those from this sum right here. So we're printing that out, and then we're printing the time that it takes to do it. Okay, so now right here is basically doing the same thing, except instead of using the sum range, I did the math right here. So there's 333 numbers between 0 and 1000 that are divisible by 3. Well, technically there's 334 if you include 0, but I'm not. So there's 3, 6, 9. The sum formula is the number of instances times the first instance plus the last, and then you divide that all by 2. So the sum of, let's say, every number between 0 and 100, or 1 and 100 will go. There's 100 numbers, so you go 100 times 1 plus 100, which is 101, and then you divide that by 2. Now 100 divided by 2 is 50, so it would be 50 times 101, which is 5,050. This is the same thing with different numbers. Okay, so you got that, and you got this right here, which corresponds to that, and then you subtract this, which is the 15, which corresponds to that. So see, 3, 5 minus 15. There's 66 numbers right here. So let's just run this, and we'll see how it checks out, what our answers are. I did this a couple of times before, just to see where it would get me. Right here, we got obviously the longest time that it take to run. And it's weird, actually, when you look at it. There must be some weird junk going on in the RAM, because each time we do this, it takes a little longer to complete. Looking back, this one took about 1/10 of a second. This one took over 2/100ths of a second. 1/100th and 2/100ths respectively. This is about 0.024. This is about 0.2. This is 0.18. This is about 0.112. So that's interesting how that's increasing. But this one is obviously the longest one in each instance. The second one and this one are roughly equal. It seems to kind of go back and forth which one actually takes longer, though. Like the first one, they seem to be increasing in length in each instance. Actually, this one decreased in length, probably. There's no memory allocation, but this one has been consistently adding a little bit each time. But these two are roughly the same, the second and third method of doing it. So if you're ever in the situation where you need to add numbers that are a multiple of a bunch, then I guess you know which method would be faster. They each take about half the time that it takes to complete the first one. So yeah, that's the answer. In each case, we got a consistent answer. As you can see, 233,168 in each instance. This one gives us a float just because of the way we used our numbers, and we'll show you that is in fact the answer, 233,168, that I entered. So thank you for watching, and I'll be continuing some other problems later. Bye.